Hello. Thank you for your patience with this kind of weird format. I'm gonna get started right away because we're gonna be recording it. What else? I think that's it. If I ask for any questions, I know a lot of you are probably on mute, so if I don't hear anything, I'm gonna assume everything is okay. On the other hand, because I'm not seeing you, I might forget to ask if there are any questions, so feel free to just unmute yourself and interject if anything does pop up. So let's just do a quick, this is last week's presentation. So last week we went over centroids and we kind of touched on center of gravity. One thing I did want to review, let's just because we introduced centroids, go right there first. So the centroid is your geometrical center. So if you were to have something that had a consistent thickness and a consistent material density, so let's say you had a rectangular beam, the centroid would also correspond with the center of gravity. It doesn't always, so let's say you had something that had a variable density to it, a material that had, let's say you had a part that had like metal BBs in it at certain pieces or something like that, that's going to have its center of gravity is going to be shifted towards where there's more weight. You can think of a centroid as, the word weight is tough, but centroid is pulling, almost think of where the majority of the area is or where the average area point would be. Let's see. So our centroids are going to determine, there's a level of stiffness or an amount of stiffness that's related to the cross section of your beam. So I mentioned last week I-beams, that I-beams are extra strong because they have more material farther away from the center. So remember that centroids are also, you can find the centroid by the by lines of symmetry if there are any. So this has two lines of symmetry, right? You have a line of symmetry down the center and line of symmetry down the across the x-axis. And so your point is going to be at the geometrical center, right? But because more weight is pulled away, it's going to have more resistance to bending. There's another element of stiffness or resistance to bending that comes from our material strength. So ultimately, it will be a combination of our material strength and the cross section of our beam or our figure that determine the thickness, the stiffness, or resistance to bending. So the first moment is that resistance based on our the geometry of our cross section. Just like our moments are with respect to a point, our first moments are going to be with respect to an axis. So it's going to be resistance to bending around that axis or along that axis. Technically, your centroid does come from integration, but through years of mathematicians and scientists, we don't have to do that integration ourselves. We have a table that has some of the centroid locations for us. So we're not going to have a square, a rectangle, a circle on this because for those ones, your centroid is going to be on the lines of symmetry. So for a rectangle, it's going to be at the halfway point. But these are ones that maybe don't have that obvious symmetry. So you have your chart, and then you also have your area, because if you remember, we used these formulas here down here to get our area. So what this is saying, your capital X bar is the X bar of your whole figure. X bar of your whole figure. It's the x centroid, so it's the centroid along the x-axis. Times the summation of area, so the area of the whole figure is equal to the summation of each individual element's x bar or its individual x centroid and the amount of area of that region. Same thing for our y centroid. You're just going to be using the y centroid values to get the y centroid of your whole figure. This one I think is a good example that just kind of shows the addition. If you have positive space or if you have material in an area, that's going to be a positive area and a positive value towards your centroid. If you have a negative space or a hole, you're going to subtract, you're going to have a negative value for your area. And ultimately, then when you multiply your centroid times your area, that's going to be a negative value as well. Okay, so that was last week. And let's take a look. I know a couple people jumped on a little late, so I'm just gonna kind of go through my spiel again. If I ask for any questions, I know you are all on mute, so if nobody says anything, I'll assume we're all good. I may also forget to ask if there are any questions because I'm not seeing you all in front of me. So if there are any, don't wait for me to ask, just jump on and interrupt me. Okay, this week we're going to be going into distributed forces or distributed loads. But let's take a look at some homework first. If you have not submitted this homework yet, it is not too late to submit it. You will get some late points deducted, but I feel like in this case, there's really not an excuse because I'm going to be going over the solutions and you have the opportunity to just do it right now and submit it. So there's no excuses on this one. It's not too late if you haven't submitted it yet. And that goes for every homework assignment. The later you wait, the lower your grade, or the more late points deducted, but it's not too late. So this one, 5.1, I don't think will be too difficult. I think we even mentioned it in class because your centroid is not always going to fall on a spot that has area. So this one, the easiest would be probably to do one rectangle. The only thing that's variable is this corner. Are you going to include it in the bottom rectangle or the side rectangle? And it doesn't make a difference what you do. So in this case, I put a vertical line. I continued this vertical line all the way down. So my first area is going to be this 30 height, and it's going to go across this 240 minus this 30 of this last portion. And then my second one is going to go this whole right side, so the full 300. Both of these are, so I found a centroid table online, but these are going to fall in the middle. So it's going to be halfway through the length and halfway through the height for each individual element. And then the area of a rectangle is base times height. You guys know I like charts. So I put everything in a chart. Do you need to do that? No, not if you can keep your data straight in your brain. So summation of area. Let's kind of remind ourselves that the formula we started with is big X bar or X bar, X centroid of the whole area times the area of the whole figure is equal to the summation of the X bars, little X bars times the area, each individual's X centroid and its area multiplied by its area. So if we have this, we can add together our two area values. Let's start with one. So the X centroid of one is going to be the halfway point of that. It was 240 minus 30, so it ends up being 105. And then it's had a 30 height, so it's 15. The thing with this one is that they do, I think most of the homework questions did give us an X and a Y axis. So we need to make sure we honor that. No matter what, you have to keep using one consistent axis system, one consistent origin point. But in this case, it's going to affect our second rectangle more. So the X bar of the second one, so the rectangle is 30 wide. So our x centroid is going to occur at 15 into that rectangle, right? But our rectangle doesn't start until 210. So our x bar is going to be that 210 plus that 15. It's always going to be with respect to the origin point, and not with respect to the start of the shape or anything like that. So that's how we get for number 225 for our x bar, and then y bar is a little more obvious probably that it's 300 high. So it's going to be halfway through that is 150. From there, you put it in your formula and it's arithmetic, right? Any questions? Homework problem 5.3. So this one you could either do a positive square plus a, well, it would still be a rectangle. It would just be a 120 by 100 rectangle, plus a triangle, or you could do a rectangle minus a triangle, right? There's variable ways you can approach these questions. A triangle, the centroid is going to be 1/3 into the triangle, closer to the longer edges. Closer to the longer edge. So in this case, it would be 1/3 in, but it would be 2/3 high because our longer edge is at the top versus at the bottom. Hopefully that makes sense. Anybody stop me if I lost you. So I'm going to follow that same process, putting all my data into a table. So our triangle, we mentioned already, it's going to be 1/3 into the x bar will be 1/3 into 1/3 to the positive x direction. So it'll be 120 over 3. So that is our 40. And then 2/3 up. So that's going to be 60 times 2 divided by 3, which also gives us a 40. And then our rectangle, it's going to be the halfway point. So x bar is going to be probably the easier one there to see is 60, 60x. And the y bar for this one is going to be halfway up the 100, but don't forget to offset that 60 that this is offset. So it's going to be 50 plus 60 is 110. Multiply, do our arithmetic, and we come to our final answers. Okay, this one's a pain, right? Okay. This one I would approach, and there are other ways of doing it, but I would approach it with a rectangle, a positive quarter circle, and a negative quarter circle. One thing to note on this one is that our y-axis is going right through the middle of, well, not the middle of the y-axis of the y-axis is going through the middle of the full thickness of it. It's not going through the centroid, but the middle of that top length. Which means that our x bar for these areas on the left are going to be negative values. Okay, so here we have a positive figure 1, a positive figure 2, and then a negative figure 3, with all of their data that comes with it. We have our quarter circle. The x bar is going to be at 4r over 3 pi. And that is relative to, so you can see the origin in this chart is right here. So that works with what we're looking at, right? So 4r over 3 pi, and then the area is pi r squared over 4. So p is pi in this case. It took me a second to read the solutions. P is pi in this case. So figure 1, its x-axis is going to be halfway through the figure, remembering that our y-axis is here. The thickness, it was 60. So the circles are a radius of 60, which means that our rectangle here is also 60 across and 120 up. So our x bar is going to be negative 30 halfway through that. Y bar is going to be positive 60. And then for our figure 2 and 3, we're going to have to use the formulas. So that would be that 4r over 3 pi. 2 is going to have a positive x-axis and a positive y-axis. To find, oh my goodness, guys, sorry, x bar and y bar, x centroid and y centroid. Note that 2, the edge that we were working from is at the top versus the bottom. So what I would do is 120, if we know this is a height of 120, I would do 120 minus 4r over 3 pi, right? Which ends up being 25.4, that value does. So the 120 minus it ends up being around 95. Note too that our third area, so we're subtracting the area, right? So the area is negative. Our x bar is also negative. When we multiply those together, we will come with a positive, right? I'm looking at this math, I'm not sure it quite out. From there, it should be down to arithmetic. Let's skip this one, because I do feel like it's not too far off from the last few ones we did. The trick would be just to make sure when you're giving your centroids of C2, that you're doing it with respect to this axis. So you're going to have to add a little bit to that, right? Or you could again go with that 30 minus whatever it is. Okay. I'll leave this here for a second, just in case you guys are going back over to review. You can pause it and take a look at the math for it. Okay, so now I feel like centroids are not my favorite thing. They're a little stale. I feel like now we start getting into a little bit more interesting things. We start seeing how the things we're learning about apply to engineering. So we get to go a little bit more towards engineering ideas. There are a couple reasons that we care about centroids. The first moment of area is that resistance to deflection that I mentioned. There's also something where you use you can get surface revolution or body of revolution, the volume of something being revolved, using a theorem that uses centroids. I think that's a calculus concept. We don't really talk about it much in this class, but it is yet another use for centroids. The one that is why I think we need to talk about centroids in this class. Well, first there's that reason that no, let's not even go there. So distributed loads are when you have a force pulling on an area rather than a point force is when there's all of force from one specific spot. So like when we had our questions, if there's any here. Like some of the old questions, where things are attached to a rope, all that force is going to be focused all that force is going to come from that point that rope is tied to, right? So that's more of like a point load, a weight pulling on one spot. Distributed loads are going to be a lot more common in like everyday objects. So like right now I have a water bottle in front of me. And when I put the water bottle down, the weight of the water and the bottle is all going consistently or at a semi-consistent pattern around the bottom of that surface. So anything, your weight on your feet is going to be distributed over the area of your feet. It's going to have huge impacts in structural engineering. Snow, wind, all those types of things are going to be applying a force over an area, right? in order to figure out where that force is focusing or impacting, where that force would, right? So we wanted to, with moments, we started talking about equivalent force moment systems, and figuring out how to get, we talked about using couples to make it easier to analyze systems. If we find the centroid, we can represent a distributed load with a point force, which will make it easier for us to analyze. And so it keeps everything consistent, but we can analyze it much more easily. See this phrase any differently. Represent loads as a concentrated force located at the centroid of the distributed load. Distributed loads do not always act on the centroid. So if there is, when I was talking about that variable weight distribution, so if all your material is the same, then you will act at the centroid if everything has a consistent density. Picture if some of this snow started melting, right? Then we're going to have a force from water and a force from snow. It's not the best example, but you would have two different systems that act on it. Again, not the best example. Hopefully I'll come up with a better one. Talk about some dialogue. Distributed loads are forces that are spread over a length, area, or volume. So we're going to use the term length only really when we're looking at 2D pictures. Load and weight density are other names that you might hear. Distributed forces, I think, is in the textbook a little bit. Most things are distributed loads. Weight of building materials, weight of adding material, force of wind, water or earth pushing on a surface, a plate underwater, a dam underwater, or anything like that, aquarium walls, forces on a straight beam. So technically, just like our centroids technically come from integration, right? If we can look at our math background, it comes from integration. Technically, our distributed loads, we can find, if we were to use this to find the area under the curve, find the centroid of that area, that would be where our distributed load is acting. Remember, integration, area under the curve are linked together. But in this class, we tend to work with shapes that we're familiar with. So right here, this is not an equation that you're going to need. I just want to kind of talk about the weight of everything, big capital W, the weight of everything or the force of everything is equal to the integration of the weight concentrated at one spot times that length dx, that length, do that integration from the beginning to the end, and that will get you where you need to go. I had a video, but I know I sometimes have issues with them if I try to do them virtually. So let me see if I can get an equivalent on YouTube and send them to you guys over announcements. Like I said, though, most of the times we're going to be working with things that, with distribution shapes, that we have easy centroid formulas for, right? So in this case, we have this beam that is between a roller and a pin joint. So A is the roller, B is the pin joint. There's a distributed load at the minimum, at the side that has the minimum force. At point A, we're getting 1,500 newtons per meter. So that is a force per length, right? At our most impacted side, or the side that has the biggest force, we're at 4,500 newtons per meter. that's newtons per length, force per length, right? So if we wanted to do this, let me just go back and no, we'll start with the centroids or with the distributed load, then we'll go to our reaction forces in a minute. So the magnitude of the force is going to be the area under the curve, right? So if let's say, so there's two ways that you could easily break this up. You could either do one rectangle at the bottom that has a magnitude of 1,500 newtons per meter times that length, and then a second area of the triangle on top, or you could do two triangles. So you see how I'm like using, think of these lines are proportional to the magnitude that they are. So picture that we're using an area to represent something that actually exists, right? Something that exists but is not so tangible. So if we talk about it in terms of area, it's going to be similar to our conversations about centroids. However, the area is going to correlate. So let's say we only had one consistent force that had, like, let's say we look at this one. And there's one consistent force. So here it has at the beginning part, it's 2 kilonewtons per meter squared. So we're in this case, they're talking about areas. Let's just say 2 kilonewtons per meter. If we were only looking at this portion of it, the centroid, the x centroid is going to fall at 2 meters because that's the centroid of the rectangle. The area is going to correlate with the amount of force that there is. So from this, in this region A to B, there are 2 kilonewtons per, let's say, meter times 4 meters. So there's total of 8 kilonewtons concentrated at the middle part. So I'm only looking in this case at portion A to B, right? Okay. Any questions? We'll keep going through with this one, but just in case. So the area is going to represent area and total force or force magnitude are going to be interchangeable in this kind of case. Know that when we say area, there's nothing physically there, but it's the same concept, right? So let's go look at, in this case, they broke it up into two triangles. So we have area 1 and area 2. Area 1 has the total height of this right here, and the total length of the 6 meters. Remember that a triangle is 1/3 towards the longer edge. When we're looking at these right now, we're only really worried about the x-axis because that's where the force is going to act on it. If you're looking at, say, here, we would be a little bit more concerned with both axes, or the y-axis. So 1/3 by closer to the longer edge. So if this is 6 meters, 1/3 of that is going to be 2, right? So the area is going to be, what is it, 1/2 base times height? Where did our chart go? 1/2 base times height, and our centroids are h/3, or whatever relative length you're looking at. So 1.5 times 6 divided by 2 is going to get you your area for that one. For your second one, you're going to follow the same process. Since your triangle is flipped, it's going to be 1/3 closer to the longer edge. So it's going to be 2/3 from the start, right? So that's where we get the 4 from there. Set up our chart the same way we would. So area under the curve is that summation of forces, or that summation of areas. Then we can set up our big X bar or our eccentric of the whole distributed load times the whole area of the distributed load or the total force. So this 18 kilonewtons equals the sum of the individual eccentroid and area or force of each system. One thing to note is if you were doing a rectangle and a triangle, so let's say area 1, you chose to use a rectangle instead, and you just have a horizontal line going all the way across, then note that your height of your triangle would then change. It would be the 4.5 minus the 1.5. That's probably the most common mistake in this one. So once we get the eccentric of the system, we know where that force magnitude is being applied to. Are there any questions? Cool. Okay. From there, let's go back to our first PowerPoint that we're looking at today and do just a little reminder of some of these. So we started introducing reaction forces, right? So the forces that we've been ignoring up to this point pretty much. We are now pretty much everything's in equilibrium from now on, and we want to know find forces that are existing physically, right? So our most common two things that we see are a pin joint and rollers in this class. We also see cables. Cables we have been using without thinking about it like this, right? Because we did our unit vectors, we were finding the direction of the physical cable, and then we were correlating that to a direction of force. So we've been doing the second row since we started. Third row, we don't really touch too much in this class. But the first row, let's think about if you had something on rollers, how is that roller going to constrain motion? So we want to introduce forces in the ways that rollers in the way that the reaction joint constrains motion. So rollers are able to move left and right. You can see that there's a pin here. I probably should have started with the pin joint. Pin joint, picture this as welded or fixed to the ground, welded, bolted, something like that. There's this linkage that has a pin going through it that also goes through what is stabilizing it to the ground. So that's going to prevent it. If we tried to pull this up, it wouldn't go because this pin would prevent it. If we tried to pull it sideways, it wouldn't go. But what it will be able to do is it'll still be able to rotate freely. So in that case, we have a constraint on our x-axis, we have a constraint on our y-axis, but we have freedom. We have freedom about the moment or rotational freedom in this area. Same thing with a rough surface, but most of the time we'll see a frictionless pin. So knowing that, if we then put a pin on a roller, how would that constrain motion? So now we're going to get that x-axis freedom back, but our motion in the y-axis, or more accurately, perpendicular to what the rollers are. So if the rollers were on a wall, it would be going this way, but perpendicular to the contact point, right? So rollers can't go through the ground, but they can slide left and right. So we're going to have a force where we are constraining or preventing motion. Okay. Any questions on that? The last one is the fixed support. So picture when you see beams in concrete or anything like that, you're going to have a rotational constraint as well, because this area down here can't rotate, right? So that's our third one there. So now let's go back to our example we were looking at. Now we got this down to where our distributed load was represented as a point load. Now we need to add in reaction forces to A and B. Reaction force at A, so rollers are going to prevent this from moving on the y-axis, but everything else is going to be able to move. So we're going to have a y-axis constraint, and B, our pin joint, is going to have an x and y constraint. So we put those in, and then it turns into a regular equilibrium type of problem. That being said, let's go back to our equilibrium stuff. So equilibrium of rigid bodies, when we're talking about points, we were talking about like a sliding motion, a translative motion. So like moving along the x-axis, along the y-axis, along the z-axis. Now we've started to look at moments, right? So with rigid bodies, if they are in equilibrium, if you had the summation of forces in x direction, summation of forces in y direction, and summation of forces in z direction, all equal to 0, but you did have a moment, your object wouldn't be sliding, it wouldn't be moving along any of the axes, but it would be spinning, it would be rotating. So in order to be truly static, truly not moving is what I wanted to say, but or consistently moving, but let's think not moving, right? That's the easiest definition for us to stick with. The summation of moments would also have to be 0. Remember that summation of moments is relative to a point. So we can evaluate any point to figure out what's going on there and try to find some unknowns. Now, if we remember that our moment comes from a force times a perpendicular distance, the two easiest points to analyze here would be either A or B. A would be, well, let's start with B. So B, the forces at B, we're going to call this By and this Bx. By and Bx both go through that point, meaning that the perpendicular distance is 0, meaning that it has no impact on the moment. Right now, our unknown values are Ay, By, and Bx. So we're getting rid of 2 unknown values and we still have 1 known value, right? We still have 1 unknown value that we're left solving for. A is going to be just as easy because remember our, I'm forgetting the name of it, but remember that we can extend a force, we can move a force along its line of action without impacting the moment. So if we were to evaluate this, the line of action goes straight through that point. The perpendicular distance is still 0 for Bx, right? So if we were analyzing the moment about point A, we would have 0 moment impact from Ay, and we would have 0 moment impact from Bx. I did both of them though. So you can see both of them there. So the summation of moments should be equal to 0, should be equal to, let's start with A. The perpendicular distance to our 18 force is that X bar that we solved for, so that 3.5. That force is going down, so this is going to cause a clockwise type of rotation, which is going to be a negative moment. So that's where we get this negative 18 kilonewtons times 3.5 meters. By is going to be acting in the opposite direction, so that's going to be a positive rotation. And we don't know the magnitude, but we do know that it's acting at a perpendicular distance of 6 away from point A. Arithmetic, we can get By. From there, we could do summation of forces in the y direction to get the other forces. I think I just wanted to show that you could do the moment about either point and get a solution. When we go in to do our summation of forces in the x direction, when we go to do our summation of forces in the x direction, there's nothing else that there are no X forces besides the reaction force at B. I still want you to put the reaction force there so that I see that you recognize that pin joints have two constraints to them, or two reaction forces associated with them, and also to see that you solved it, to get that it's equal to 0. So even though we're probably going to see this a lot in this unit, I still want you to always kind of write it out and think it out and make sure that it really truly is. Now, what was the thought that I had that distracted myself? Just kind of an aside about problem solving. So if you're somebody who is not good with moments, who doesn't totally understand them 100%, you would probably want to do one summation of moment because it's unavoidable. You have to do it at least once. But then for the other one, you could do, say, summation of forces in the y direction. So let's say we solved for By, and then we did summation of forces in the y direction. It's going to be Ay minus 18 plus By, which we end up getting to be this value. So we're going to end up with the same Ay of 7.5. So pick an approach that you feel more comfortable with, just to minimize what kind of error we might get with it, right? Are there any questions here? The last one, we have a sample problem that includes water. We're not going to be working with water too much in this class. I did just want to highlight that there is a problem about water, and that going into your dynamics class, you probably will start using distributed loads for water pressure, right? So just at the top of water, we know that as you get deeper in water, the pressure increases, right? Which is why there's like, people get sick if they come up from scuba diving too fast or anything like that. And the things at the bottom of the ocean are creepy. But so we're starting from a lesser amount of pressure. We'll find out in your fluid dynamics class probably that pressure and depth have a linear relationship. So we're going to have a linear distributed load going down. I think I just wanted to kind of show this problem too, to show how many elements. So this is concrete base, right? So it's going to be hard for this to rotate. So there is going to be that constraint, that moment constraint introduced as well. You would have to break it up into shapes that you recognize. This is one that is on the chart. So I just wanted to kind of highlight this problem. There's no difference in how you would approach it versus any other distributed load problem. That being said, are there any questions? Cool. Let's take a look at some homework questions. We are not going to be doing these together, but we will take a look at them. Okay, so at A, that's going to be essentially that fixed support that we were looking at, right? It looks kind of similar. You're not seeing the underground type of view of it. But for beam with loading shown, determine A, the magnitude and location of the resultant of the distributed load, and B, the reactions of the beam support. So we're going to approach this the same way we approach the other one. You could either do two triangles or a rectangle and a triangle for your distributed load. Your reactions at A, your reaction forces at A, because it's at fixed support, you're going to have a constraint in the X direction, the Y direction, and rotationally. So you're going to have all three reaction forces there. So you might want to do AY, AX, and maybe the M of A or something like that, moment at A. And that would be your approach here. This one's a little bit backwards looking. Same type of thing. This one's probably easier to do a rectangle and then a triangle. So then remember, if you do that, if you were to do that, your rectangle would be 40 pounds per inch all the way across this 10 inches. So for your triangle area, it would be important to remember that the maximum height would then be 90 pounds per inch minus 40 pounds per inch, right? Because this is already counted. You can only count an area once. If you count it twice, it's gonna mess up your results. B is gonna be that same type of fixture as A is here, right? So our beam is gonna have constraints in the X and Y direction and rotationally. So there's gonna be a moment there as well. You might hear sometimes the term degrees of freedom. Degrees of freedom are where how your thing can move. So like a roller is gonna have, if you had a roller on the y-axis, so B is going to have and a degree of freedom along X and a rotational degree of freedom. The y-axis is constrained, so there is no freedom there. Just to kind of introduce a little extra verbiage and whatnot. This one, you're gonna kind of have to do a little bit of the math of lengths and whatnot, but that's half the fun. So A is a pin joint. So our X and Y axis are both going to be constrained, whereas B is a roller. So only our Y axis is going to have a constraint. And then our last one is this one. So B is going to be the same as it was in these previous, the first two. Are there any questions on that? Does anybody have any questions about anything in general? I did grade the tests. Your grades are posted. I didn't want to review them online. Just, you know why. So that'll be next week. That being said, I did finish super early. And I know that I had a question from a student about in old homework. I wanted to take, it's a little bit old, but if there are no questions, we can go take a look at it. Any questions? Homework 5. Okay. Okay. Let's start with these. I don't know that I want to go through all of these. But this is a good one to reference when we're talking about finding the reaction supports. Okay, so let's take a look at this. Replace each loading with equivalent force coupled system at the end of it. You know what? I think I thought this was a different homework. So I'm gonna pull back on that. Any questions? Okay, cool. Who's this? No, okay. I'm good then. If you guys are good, I'll stick around for any more questions or anything like that, but I'm gonna stop the recording.